All right, so welcome to section 3.8, related rates. And we are here doing this in a live class session. But yeah, we're also recording it for y'all on YouTube. So in related rates here, the big idea behind this section is that we are going to be looking at two or more quantities. So we have two or more quantities. They're going to be represented by variables, price. So we have two or more quantities that are changing. Oops, let me make that look nice. Changing. And we got to work some rates into this. So their rates of change are related. Okay, so one quantity is affecting the other. Their rates of change are related, and that's how we get the name of the section, related rates. The rates are related. And these rates of change, as someone mentioned in our chat when the recording was off, these rates of change are going to be instantaneous rates of change. So we're going to be looking at derivatives here. So these are derivatives with respect to time. So time or the variable t. And that's why in the warm-up problems, we were doing some implicit derivatives with respect to the variable t, where all your variables were a function of t. And then we were taking derivatives with respect to t. We were making rates of change with respect to time. Okay. So that's the big idea. And we're really going to jump straight into some examples here. But here's what's going on in our notes packet. We've got a bunch of example problems. We'll start with the first one in just a minute. There is a general procedure for you right here for how to solve a related rates problem. We'll go through this step by step so you can see how to use it. You don't need to memorize this like with the numbers or anything, but you do need to know how to solve problems of this type. So there's some guidelines for you. We'll fill in this next part here, some common relationships and equations. You'll see what that's all about. Then there's also a page of geometry formulas for you guys in this section. Just in case it's been a little while since you've done any geometry, you'll find that some of these formulas are going to be useful for problems in this section. So if you need to refresh, there's a little refresher for you. All right, so we're going to take a look at our first problem here. I've copied it so there's more space. We'll need it. And the problem here says that a bouillon cube is placed into a pot of boiling water. And if anyone is not familiar with this word right here, bouillon, that is like a soup cube thing. It's used to make broth, like kind of a ramen type broth usually, or just like a beef broth, chicken broth, vegetable broth. Yeah, it's just one of those little compact cubes that make soup. Okay, so we're making soup. We put a bouillon cube into some boiling water. Assuming that it roughly resembles a cube as it dissolves, at approximately what rate is its volume changing when its side length is 0.25 centimeters and decreasing at a rate of 0.12 centimeters per second? So there's a lot of information in here, and we'll walk through how to break that down and use it. But basically, where we want to start with this is drawing a picture of our scenario. That's step one in our problem solving process here. Oops. To sketch the scenario, we're going to label that sketch and identify what we want to find. Some little notes here. What is a constant? What is variable? And we need to name our variables. Okay. So basically, for our problem here, we need to sketch a Boolean cube. And we do make a pretty wild assumption here, assuming that it stays cube shaped as it dissolves. If you've ever made soup from a bouillon cube, it kind of turns into a lump of mush. But for the sake of this problem, we're going to assume that it stays roughly cube shaped. All right, so we need to draw our cube. Okay. So we sketch our little situation here of the soup cube. Fix that little line. Okay. And we need to label this as well for things that are constant and things that are variable. Well, nothing is really staying constant on this. It's shrinking, all the sides are changing, but it's staying in that cube shape. We don't have any constants to label here, but we do want to label the sides of this cube as variable because they're changing. Anything that changes is going to get a variable name. So I am creatively going to call the sides of the cube S for side. So since it's a cube, they're all three the same. So S, S, and S. Okay. Now we want to identify what we're trying to find here. This is not always a required step of these related rates problems, but I find it's very useful, especially when you're first starting out. Because sometimes it's hard to tell when you're done with these problems. And so it's good to identify where you want to get to so that you know when you've gotten there. All right. So off to the side, we'll just write a little statement of what we want. And notice that the problem is asking at approximately what rate is its volume changing? So that's what we are trying to find, a rate of volume change at a particular point in time. So mathematically, for you guys on the live session, how could we express a rate of volume change? Let's see if they've got any guesses here. You might take some inspiration from our warm-up problems, maybe. Instantaneous rate of change. All right, looks like no takers at the moment, but remember we're looking at instantaneous rates of change with respect to time here. So for volume, we can go ahead and call that V. We'll assign it a variable here. So we'll get our rate of change of volume with respect to time. dV dt, derivative of volume with respect to time, that's our rate of volume change. Okay. So that's what we're looking for. We want dV dt, and then this is at just a instantaneous point. Let's see. Let's see in the chat there. We have a comment here, not a derivative of an instantaneous rate of time. Not quite sure what you mean by that. So if you want to clarify in the chat there, I'll keep an eye on it. But we do have an instantaneous rate of change here with that derivative. But we do need to identify the instant where we want this rate of change. So that's what we're going to do with the next part here. Because the instant that we're looking at is exactly when the side length is 0.25 centimeters. So we want dV dt, our instantaneous rate of change, at exactly that instant. So when the side length S is 0.25 centimeters. So there's our instantaneous rate of change at this instant. Right? We'll see if that helps a little bit. So instantaneous rate of change at a particular instant. Okay. Now there is another number in here. The side length is 0.25 centimeters, and then we also have this idea of decreasing at a rate of 0.12 centimeters per second. That you'll notice is also a rate of change with respect to time there. 0.12 centimeters per second. So that we're also given that at this instant, our rate of change in the side length is decreasing at 0.12 centimeters per second. So we are given the rate of change of the side length over time at that instant. And it's 0.12 centimeters per second, but you'll want to note that this is decreasing, which is going to give us a negative rate of change. Okay, so negative is because it's decreasing there. All right, so at the instant when the side length is 0.25 centimeters, the instantaneous rate of change of side length is negative 0.12 centimeters per second. All right. So still keeping half an eye on the chat here. Let's see. But this is identifying what we want to find. Now, for the next step of this problem, or any related rates problem, we're going to find an equation to relate our quantities of interest. Okay, and it says to just try something. Maybe our first guess doesn't work. Sometimes it will. Okay, we just need to find something related to what we're looking at here. Okay, so our quantities that we're interested in are volume, for sure, because that's something that we want, rate of change of volume. And then another quantity that we're looking at is side length. We have a given instant with the side length at that instant, and we also know a rate of change of side length. So our quantities are really volume and side length. So the equation to relate those would be the volume of a cube. V equals S cubed. Okay, we'll work with that. Let's see what the next step is. Step 3. All right, we need to get some rates in here. We're going to differentiate that equation we just came up with respect to time t, and this is going to be an implicit derivative. Okay, so we got to do both sides of the equation, and we're going to create some rates in doing so. All right, so we're taking derivative with respect to time t of v, and then derivative with respect to time t of s cubed. Okay, so this left-hand side, we saw something like that in the warm-ups. Okay, that's going to be our dv dt. And then on the right-hand side, derivative with respect to t of s cubed. That one, we've got to use a little tiny chain rule on that. So if anyone beats me to it in the chat, you are welcome to. But remember, you do the fact that s is really a function of t. Okay, so d dt of 3s getting cubed. And yes, someone beat me to it. Nice. So 3s, and then I think there should be a little squared there, right? Right? 3s squared and ds dt. Yeah, awesome. So yeah, okay, good. 3s squared, we got it. ds dt. Okay, cool. So yeah, we have created an equation involving the two rates here. This is the rate of change of volume. So IROC, instantaneous rate of change of volume. And then ds dt is the instantaneous rate of change of the side length s. Okay, so this equation essentially relates the two rates that we're interested in. So this is how the rates are related. So related rates, yay. The rates are related. And how are they related? According to this equation. So the rates are related according to this equation after we've taken the derivative. Okay, cool. So if we look at, just to kind of refresh what we want to get out of this, we want to find dv dt when s is 0.25 centimeters and ds dt is 0.12 centimeters per second. So let's plug those in. All right. Plug in the things that we know we want at that instant. So we're going to have dv dt. We don't have a value for that, and that's actually good because that's what we're looking for. That'd be 3s is 0.25 centimeters. I'll go ahead and put the units in here as well. 0.25 centimeters getting squared, and then times ds dt, negative 0.12 centimeters per second. Okay. So if we calculate what we've got here, dv dt, and definitely feel free to use a calculator on these. If you're supposed to round to a certain number of decimal places, I will let you know if it's on a quiz or a test or something, because yes, this will be on your Module 3 test. And on my math lab, they should clarify what they want you to round to. If they don't and you're off by a rounding error, remember that you can just send me the problem and I'll check it out for you and give credit where credit is due. Okay, so you'd put this into your calculator and we come out with negative 0.0225 for a value. And for the units, notice how we have centimeters squared here, and then times another centimeter per second. So that'd be centimeters cubed per second. Okay. And that is our answer for the change in volume over time, the instantaneous rate of change of volume, that is, at this particular instant. Now, the last step in each one of these problems is to check your answer and make sure that it actually makes some sense here. And first thing, we could check the units on this and notice that it actually does make sense for a rate of change of volume. Centimeters cubed is a volume measurement over time. So yeah, we got the right type of units for what we're looking for here. So units make sense. Okay, check. You'll want to look at the value that you're getting. And I mean, you don't have to know like, oh, does this exact number make sense? But just kind of ballpark wise, does it make some sense? And I would say, yeah, because it's a pretty small value. And a bouillon cube, soup cube, is really small, especially with the size measurements we're looking at this instant, 0.25 centimeters for a side length. So yeah, in the chat there, does it fit the example? That's exactly what we're looking for here. Yeah. If this was saying like it was changing at 5,000 cubic centimeters per second, we would have a bit of a problem there because that would be not realistic at all. So value, yeah, the size makes some sense. And then also the fact that it's negative makes some sense as well, because that means that it's decreasing. So negative implies decreasing. And yeah, our volume is decreasing because the cube is getting smaller. So yeah, in the chat there, someone put like 0.000001 centimeters cubed per second. That one might seem a little on the small side for this. So yeah, it's just kind of like ballpark estimates. Does the value seem appropriate? Yeah. So yeah, I'd say the size seems somewhat fitting there, and the negative indicates that it's decreasing. That makes some sense. And so we seem to have a reasonable answer, and in fact, it is the correct answer. So yeah, there's our rate of change of volume over time at that particular instant. So there's the whole big picture there. And I'll go ahead and pause our recording here, and we'll pick up at the next one.